What if everything we see in the universe, the stars, the galaxies, the swirling cosmic dust, is just the tip of the iceberg? What if the vast majority of the universe is made up of something we can't see, can't touch, and barely understand? This invisible force, known as dark matter, is one of the most profound mysteries in all of science. It doesn't emit light, it doesn't reflect it, and yet it holds the cosmos together like an unseen hand. Without it, galaxies would fly apart, stars would scatter, and the universe as we know it would cease to exist. But here's the thing, we still don't know what dark matter actually is. It's a ghostly presence that shapes the universe, yet it remains completely hidden from our eyes. Today, we're diving into the cosmic dark matter web, the invisible architecture that connects everything in the cosmos. Over the course of this video, we'll unravel 25 mind-bending mysteries about this enigmatic substance, from its role in galaxy formation to its connection to black holes and even its potential ties to other universes. So, if you're ready to explore the unseen forces that govern our reality, stay with us. The journey into the cosmic unknown begins now. Now, let's take a closer look at the invisible architecture of the universe, the cosmic dark matter web. Picture the universe not as a random scattering of galaxies, but as a vast, intricate network, like a spider's web stretching across the cosmos. This web is made up of dark matter, the unseen scaffolding that holds everything together. Without it, the universe would be a chaotic mess with galaxies drifting aimlessly through space. But thanks to dark matter, galaxies are connected by these invisible threads, forming clusters and superclusters that make up the large-scale structure of the universe. So, how does this web work? Imagine dark matter as the framework, the skeleton of the cosmos. It's everywhere, but it doesn't interact with light or any form of electromagnetic radiation, which is why we can't see it directly. Instead, we know it's there because of its gravitational effects. Galaxies orbit faster than they should based on the visible matter alone, and the way light bends around massive objects tells us there's something invisible at play. This is the dark matter web in action. Its gravitational pull shapes the paths of galaxies, guiding them into the filaments and nodes of this cosmic network. But here's the challenge. Detecting something that doesn't emit, absorb, or reflect light is no easy task. Scientists rely on indirect methods, like observing how light bends around massive objects or studying the motion of stars within galaxies. These clues help us map the dark matter web, but it's like trying to trace the outline of a shadow. We can see its influence, but the substance itself remains elusive. This invisible architecture is the backbone of the universe, and yet it's one of the hardest things to study. As we move forward, we'll explore how this mysterious web not only connects galaxies, but also plays a crucial role in their formation and evolution. The cosmic dark matter web is more than just a hidden structure. It's the foundation of everything we see in the universe, and understanding it could unlock some of the deepest secrets of the cosmos. Now, let's step back in time to uncover one of the first major clues that hinted at the existence of dark matter, the missing mass problem. This mystery began in the 1930s when a Swiss astronomer named Fritz Zwicky made a groundbreaking observation. While studying the Coma cluster, a massive group of galaxies, Zwicky noticed something strange. The galaxies within the cluster were moving much faster than they should have been, based on the amount of visible matter present. According to the laws of gravity, the combined mass of all the stars, gas, and dust in the cluster wasn't nearly enough to explain the speeds at which these galaxies were orbiting. It was as if there was an invisible force holding everything together, something that couldn't be seen but was undeniably there. Zwicky called this unseen mass dark matter, a term that would go on to become one of the most important in modern cosmology. His discovery was met with skepticism at first, as the idea of invisible matter seemed almost too fantastical to believe, but over time more evidence began to pile up. In the 1970s, astronomer Vera Rubin and her team observed similar discrepancies in the rotation speeds of stars within individual galaxies. Stars on the outer edges of galaxies were moving far too quickly to be explained by the visible matter alone. This reinforced the idea that something invisible, dark matter, was providing the extra gravitational pull needed to keep these stars from flying off into space. So, what does this mean? Essentially, the missing mass problem revealed a glaring gap between what we could see and what we could measure. The visible universe, stars, planets, gas, and dust accounts for only a small fraction of the total mass needed to explain the gravitational effects we observe. The rest, scientists concluded, must be made up of dark matter. This invisible substance doesn't interact with light, making it impossible to detect with traditional telescopes. Yet, its gravitational influence is undeniable, shaping the motion of galaxies and the structure of the universe itself. The discovery of the missing mass problem was a turning point in our understanding of the cosmos. It forced scientists to rethink the nature of matter and led to the realization that the universe is far more complex than we once thought. As we continue to explore the mysteries of dark matter, Zwicky's observations remain a cornerstone of modern astrophysics, reminding us that sometimes the most profound discoveries come from what we can't see. Next, we'll dive into how dark matter plays a crucial role in the formation of galaxies, shaping the universe as we know it today. Now, let's shift our focus to one of the most fascinating aspects of dark matter, its role in the formation of galaxies. Without dark matter, the universe as we know it would look entirely different. In fact, galaxies as we see them today simply wouldn't exist. But how does this invisible substance play such a crucial part in shaping the cosmos? To understand this, we need to go back to the early universe just moments after the Big Bang. At that time, the universe was a hot, dense soup of particles and energy. As it expanded and cooled, tiny fluctuations in density began to emerge. These fluctuations were like seeds, and dark matter was the soil in which they grew. Because dark matter doesn't interact with light or other forms of electromagnetic radiation, it was able to clump together under the influence of gravity long before ordinary matter could. These clumps of dark matter formed the first gravitational wells, pulling in gas and dust over time. As ordinary matter, like hydrogen and helium, fell into these wells, it began to heat up and collapse, eventually igniting to form the first stars. These stars, along with the gas and dust, were held together by the gravitational pull of the dark matter halos surrounding them. Without dark matter's gravitational scaffolding, the gas would have simply drifted apart and stars would never have formed in the first place. Over billions of years, these early star-forming regions grew into the galaxies we observe today, from spirals like our Milky Way to massive ellipticals and irregular galaxies. But dark matter's influence doesn't stop there. It also plays a key role in maintaining the structure of galaxies over time. For example, the rotation curves of galaxies. How fast stars orbit around their centers reveal that the outer regions of galaxies rotate much faster than they should if only visible matter were present. This is where dark matter steps in. Its gravitational pull keeps these stars from flying off into space, ensuring that galaxies remain stable and intact. In essence, dark matter is the unseen architect of the universe, providing the gravitational framework that allows galaxies to form, grow, and endure. Without it, the cosmos would be a far emptier and less structured place. As we continue to explore the mysteries of dark matter, we gain a deeper appreciation for its profound impact on the universe's evolution. Next, we'll delve into the elusive nature of dark matter particles and why they've remained so difficult to detect despite decades of research. Now, let's turn our attention to one of the most puzzling questions in modern physics. What exactly is dark matter made of? Despite decades of research, scientists have yet to directly detect the particles that make up this mysterious substance. The search for dark matter particles has led to some fascinating theories, but it has also revealed just how elusive these particles truly are. One of the leading candidates for dark matter particles is something called weakly interacting massive particles, or WIMP. These hypothetical particles are thought to be heavy, slow-moving, and interact with ordinary matter only through gravity and the weak nuclear force, one of the four fundamental forces of nature. Because of their weak interactions, WIMP would rarely collide with ordinary matter, making them incredibly difficult to detect. Scientists have built highly sensitive detectors deep underground, shielded from cosmic rays and other interference, hoping to catch a glimpse of these elusive particles. Yet, despite these efforts, WIMP remain undetected. Another promising candidate is the axion, a particle that was originally proposed to solve a completely different problem in particle physics. Axions are thought to be extremely light and interact even more weakly with ordinary matter than WIMP. They could be streaming through the universe in vast numbers, completely unnoticed. To detect axions, researchers have designed experiments that use strong magnetic fields to convert them into detectable photons. But so far, these experiments have also come up empty-handed. So, why has dark matter remained so stubbornly hidden? One reason is that dark matter particles, if they exist, might interact with ordinary matter in ways we don't yet understand. They could be far lighter or heavier than we expect, or they might interact through forces we haven't discovered yet. Another possibility is that dark matter isn't made of particles at all, but something entirely different, like tiny black holes or even defects in the fabric of spacetime. The search for dark matter particles is a bit like trying to find a needle in a cosmic haystack, except we're not entirely sure what the needle looks like or if it's even there. Despite the challenges, scientists remain determined. Every experiment, whether it succeeds or fails, brings us closer to understanding the true nature of dark matter. As we continue to push the boundaries of technology and theory, we may one day uncover the secrets of these elusive particles and finally solve one of the universe's greatest mysteries. Next, we'll explore one of the most compelling pieces of evidence for dark matter, the bullet cluster, and how it provides a smoking gun for the existence of this invisible cosmic architect. Now, let's shift our focus to one of the most striking pieces of evidence for dark matter, the bullet cluster. This cosmic phenomenon isn't just a spectacular collision of galaxy clusters, it's a smoking gun that has fundamentally reshaped our understanding of the universe's invisible architecture. The bullet cluster is the result of two massive galaxy clusters slamming into each other at incredible speeds, creating a cosmic spectacle that reveals the hidden hand of dark matter. Here's what makes the bullet cluster so extraordinary. When these clusters collided, their hot gas clouds made of ordinary, visible matter crashed together and slowed down due to friction, creating a shock wave that glows brightly in X-rays. But something else happened that caught scientists by surprise. The galaxies within the clusters, along with something invisible, kept moving forward, seemingly unaffected by the collision. This invisible component, dark matter, how do we know this? Using a technique called gravitational lensing, astronomers were able to map the distribution of mass in the bullet cluster. Gravitational lensing occurs when massive objects like galaxy clusters bend the light from background galaxies, distorting their images. By analyzing these distortions, scientists could pinpoint where the majority of the mass was located. And here's the kicker: the mass wasn't where the visible matter was. Instead, it was concentrated in regions where there was no glowing gas or stars, only dark matter. This separation between visible matter and dark matter is a game changer. It shows that dark matter doesn't interact with light or ordinary matter in the same way. While the hot gas clouds collided and slowed down, dark matter passed right through, unaffected by the forces that govern visible matter. This behavior is exactly what we'd expect from a substance that only interacts through gravity, providing some of the strongest evidence yet for the existence of dark matter. The Bullet Cluster isn't just a cosmic accident, it's a natural laboratory that has given us a rare glimpse into the behavior of dark matter. It's a reminder that the universe is full of surprises, and sometimes the most profound discoveries come from observing the aftermath of cosmic chaos. As we continue to study collisions like this one, we're piecing together the puzzle of dark matter, one cluster at a time. Next, we'll explore how supercomputer simulations are helping us visualize the vast, invisible network of the cosmic dark matter web. Now, let's take a step into the digital realm where cutting-edge technology meets the mysteries of the cosmos. Supercomputer simulations have become one of the most powerful tools in our quest to understand the cosmic dark matter web. Among these, the Millennium simulation stands out as a groundbreaking achievement, offering us a virtual window into the universe's hidden architecture. Imagine trying to map out the largest structures in the universe, structures so vast they span billions of light years. This is no small task, but supercomputers like those used in the Millennium simulation have made it possible. By crunching mind-boggling amounts of data, these simulations recreate the universe's evolution over billions of years, starting from just moments after the Big Bang. They allow us to see how dark matter, driven by gravity, clumps together to form the intricate web-like structure that connects galaxies and galaxy clusters. What's truly remarkable is how closely these simulations match what we observe in the real universe. When astronomers map the distribution of galaxies and compare it to the simulations, the resemblance is striking. The filaments, nodes, and voids predicted by the simulations align almost perfectly with the patterns we see in the night sky. This alignment gives us confidence that our understanding of dark matter and its role in shaping the universe is on the right track. But how do these simulations work? At their core, they rely on the laws of physics, particularly gravity, to model how dark matter behaves over time. Starting with a nearly uniform distribution of dark matter in the early universe, the simulations track how tiny fluctuations grow into massive structures. These structures form a cosmic web with dense regions where galaxies form and vast, empty voids in between. The Millennium simulation, for example, followed the evolution of more than 10 billion particles of dark matter, creating a virtual universe that mirrors our own. These simulations aren't just impressive feats of technology, they're essential tools for testing our theories about the universe. They help us predict where dark matter should be and how it influences the formation of galaxies. They also allow us to explore what-if scenarios, like how the universe might look if dark matter behaved differently. By comparing these virtual universes to real observations, scientists can refine their models and uncover new insights into the nature of dark matter. The Millennium simulation and others like it have transformed our understanding of the cosmic dark matter web. They've shown us that the universe's large-scale structure isn't random. It's the result of dark matter's gravitational pull, weaving a vast, invisible tapestry that connects everything we see. As we continue to improve these simulations, we're getting closer to unraveling the secrets of dark matter and the universe itself. Next, we'll dive into the mysterious halos of dark matter that surround galaxies and how they shape the cosmos in ways we're only beginning to understand. Now, let's shift our focus to the mysterious halos of dark matter that envelop galaxies like invisible cocoons. These halos are vast, spherical clouds of dark matter that extend far beyond the visible edges of galaxies, playing a crucial role in shaping their behavior and structure. But what exactly are dark matter halos, and why are they so important to our understanding of the cosmos? To start, imagine a galaxy like our Milky Way. What we see through telescopes, the stars, gas, and dust, is just the tip of the iceberg. Surrounding this visible material is a massive halo of dark matter, stretching hundreds of thousands of light years into space. This halo is invisible to our instruments because dark matter doesn't emit, absorb, or reflect light. Yet, its presence is undeniable thanks to its gravitational effects. One of the most compelling pieces of evidence for dark matter halos comes from the way galaxies rotate. In the 1970s, astronomer Vera Rubin made a groundbreaking discovery while studying the rotation curves of galaxies. She found that stars on the outer edges of galaxies were moving just as fast as those near the center, defying expectations based on Newton's laws of gravity. If galaxies were made only of visible matter, the outer stars should slow down as they move farther from the galactic center, but they don't. This discrepancy led scientists to conclude that something invisible, dark matter, must be providing the extra gravitational pull needed to keep those stars moving at such high speeds. Dark matter halos are the key to solving this mystery. They act like an invisible scaffold, holding galaxies together and influencing their rotation. Without these halos, galaxies would fly apart, unable to maintain their structure. The gravitational pull of the dark matter halo keeps stars, gas, and dust in orbit, ensuring the galaxy remains intact. But why can't we see these halos directly? The answer lies in the nature of dark matter itself. Unlike ordinary matter, dark matter doesn't interact with electromagnetic forces, meaning it doesn't produce or interact with light. This makes it completely invisible to telescopes, no matter how advanced they are. Instead, we detect dark matter halos indirectly through their gravitational effects on visible matter and light. For example, when light from distant galaxies passes through a dark matter halo, it bends due to the halo's gravity, a phenomenon known as gravitational lensing. This bending of light provides a kind of shadow that reveals the presence of dark matter. The study of dark matter halos has also revealed another fascinating aspect: their role in galaxy formation. These halos act as cosmic nurseries, providing the gravitational framework needed for gas and dust to accumulate and eventually form stars and galaxies. Without dark matter halos, the universe as we know it, filled with galaxies, stars, and planets, simply wouldn't exist. As we continue to explore these invisible structures, we're uncovering more about their complexity and influence. Dark matter halos aren't uniform. They vary in size, shape, and density depending on the galaxy they surround. Some halos are smooth, while others are clumpy, reflecting the chaotic processes that shape them over billions of years. Understanding these variations is crucial for piecing together the full story of how galaxies form and evolve. The mystery of dark matter halos is far from solved, but each discovery brings us closer to understanding their true nature. These invisible giants are not just passive observers in the cosmic dance, they're active participants, shaping the universe in ways we're only beginning to comprehend. Next, we'll explore the intriguing connection between dark matter and dark energy, and how these two enigmatic forces work together to shape the fate of the cosmos. Now, let's turn our attention to the intriguing relationship between dark matter and dark energy, two of the most mysterious forces shaping the universe. While dark matter holds galaxies together with its gravitational pull, dark energy works in the opposite direction, driving the accelerated expansion of the cosmos. Together, these invisible forces play a pivotal role in determining the fate of the universe, but their connection remains one of the greatest puzzles in modern cosmology. To understand this connection, let's first revisit what we know about dark energy. Discovered in the late 1990s, dark energy is the mysterious force causing the universe to expand at an ever-increasing rate. Unlike dark matter, which pulls matter together through gravity, dark energy seems to push space itself apart. This discovery was a shock to scientists who had long assumed that the universe's expansion would slow down over time due to gravity. Instead, observations of distant supernova revealed that the expansion is speeding up, pointing to the existence of something entirely unexpected: dark energy. So, how do dark matter and dark energy interact? On the surface, they seem like opposites. Dark matter's gravity binds galaxies and galaxy clusters together, while dark energy's repulsive force drives them apart. Yet, these two forces are deeply intertwined in shaping the large-scale structure of the universe. Dark matter provides the scaffolding for galaxies and galaxy clusters to form, while dark energy dictates how quickly these structures move away from each other as the universe expands. Without dark matter, galaxies wouldn't have formed in the first place. Without dark energy, the universe's expansion wouldn't be accelerating, and its future would look very different. One way to think about their relationship is to imagine the universe as a giant cosmic tug-of-war. Dark matter is the anchor, holding everything in place, while dark energy is the force pulling the rope, stretching space itself. The balance between these two forces determines how the universe evolves over time. In the early universe, dark matter dominated, allowing galaxies and galaxy clusters to form. But as the universe expanded and matter spread out, dark energy began to take over, pushing galaxies apart faster and faster. This interplay between dark matter and dark energy also influences the universe's ultimate fate. If dark energy continues to dominate, the universe will keep expanding at an accelerating rate, eventually leading to a scenario known as the Big Freeze, where galaxies are so far apart that the universe becomes cold and empty. On the other hand, if dark energy's influence weakens or changes over time, the balance could shift, potentially altering the universe's trajectory. Understanding the connection between these two forces is key to predicting what lies ahead for the cosmos. Despite their importance, both dark matter and dark energy remain shrouded in mystery. We don't yet know what they're made of or how they originated. Some theories suggest that dark energy could be a property of space itself, often referred to as the cosmological constant, while others propose that it's a dynamic field that changes over time. Similarly, dark matter's true nature, whether it's made of particles like WIMP or something entirely different, is still unknown. What's clear, however, is that solving the mystery of their connection could unlock some of the deepest secrets of the universe. As we continue to explore this cosmic puzzle, new observations and experiments are shedding light on how dark matter and dark energy shape the universe. From mapping the distribution of galaxies to studying the cosmic microwave background, scientists are piecing together clues that could reveal how these two forces interact. Each discovery brings us closer to understanding not just the universe's past, but also its future. Next, we'll dive into the search for dark matter in space, exploring how cutting-edge experiments are hunting for this elusive substance beyond the confines of Earth. Now, shifting our gaze beyond Earth, let's explore how scientists are searching for dark matter in the vast expanse of space. Unlike traditional experiments conducted on the ground, space-based missions offer a unique vantage point to hunt for this elusive substance. One of the most prominent tools in this cosmic search is the Fermi Gamma Ray Space Telescope, a powerful observatory designed to detect high-energy gamma rays. These gamma rays could hold the key to uncovering dark matter, as some theories suggest that dark matter particles might produce gamma rays when they collide and annihilate each other. The Fermi telescope scans the sky, searching for faint signals that could point to the presence of dark matter. One area of particular interest is the center of our galaxy, the Milky Way, where dark matter is thought to be densely concentrated. If dark matter particles are indeed annihilating, the resulting gamma rays could create a detectable glow. However, distinguishing these signals from other sources of gamma rays, such as pulsars or black holes, is a significant challenge. The universe is filled with high-energy phenomena, and isolating dark matter's signature requires precise measurements and sophisticated data analysis. Another promising approach involves studying dwarf galaxies, which are small, faint galaxies orbiting the Milky Way. These galaxies are rich in dark matter but contain very little ordinary matter, making them ideal laboratories for dark matter detection. By observing gamma rays from these galaxies, scientists hope to find evidence of dark matter interactions. Yet, even here, the signals are incredibly faint, requiring years of observation and careful analysis to separate potential dark matter signals from background noise. Detecting dark matter in space also presents unique technical challenges. Space-based instruments must operate in extreme conditions, enduring intense radiation and temperature fluctuations. Additionally, the vast distances involved mean that signals from dark matter interactions are incredibly weak by the time they reach us. This makes it essential to design highly sensitive detectors and develop advanced algorithms to sift through the data for meaningful patterns. Despite these challenges, space-based experiments like Fermi are pushing the boundaries of our understanding. They complement ground-based efforts, offering a broader perspective on the universe and increasing the chances of a breakthrough. As technology advances, future missions may provide even more powerful tools for this cosmic hunt, bringing us closer to solving one of the greatest mysteries in science. Next, we'll venture underground to explore how scientists are using some of the most sensitive detectors ever built to search for dark matter particles deep beneath the Earth's surface. Now, let's take a journey beneath the Earth's surface, where scientists have built some of the most advanced laboratories in the world to hunt for dark matter. Deep underground, far from the interference of cosmic rays and other background noise, experiments like LUX Zeppelin and Xenon 1T are quietly searching for the faintest traces of this mysterious substance. These detectors are designed to be incredibly sensitive, capable of picking up signals that would otherwise be drowned out by the chaos of the surface world. But why go underground? The answer lies in the need for extreme isolation. On the surface, our planet is constantly bombarded by particles from space, creating a noisy environment that makes it nearly impossible to detect the subtle interactions of dark matter. By placing detectors deep underground, scientists can shield them from this interference. Thick layers of rock act as a natural barrier, filtering out unwanted particles and allowing the detectors to focus solely on the rare events that might signal the presence of dark matter. LUX Zeppelin, one of the most sensitive dark matter experiments ever built, is located nearly 1 mile underground in a former gold mine in South Dakota. It uses liquid xenon as its detection medium, a material chosen for its ability to produce tiny flashes of light when a dark matter particle interacts with it. Similarly, Xenon 1T, located beneath the Gran Sasso mountain in Italy, also relies on liquid xenon to capture these elusive interactions. Both experiments are designed to detect the faint recoil of a xenon atom when it collides with a dark matter particle, a process so rare that it might happen only a handful of times over years of observation. The extreme environments of these underground labs are crucial for another reason. They allow scientists to control every possible variable. Temperature, humidity, and even the slightest vibrations can affect the detector's performance. By operating in such controlled conditions, researchers can ensure that any signal they detect is truly from dark matter and not from external factors. It's a painstaking process, but one that could finally bring us face to face with the universe's most elusive substance. As we continue to push the boundaries of technology and ingenuity, these underground experiments represent some of our best hopes for uncovering the secrets of dark matter. Next, we'll explore another intriguing aspect of this cosmic mystery, the debate over whether dark matter is cold or warm, and what that means for the structure of the universe. Now, let's turn our attention to a fascinating debate that has puzzled scientists for decades: the temperature of dark matter. Is it cold or is it warm? This might sound like a simple question, but the answer has profound implications for how we understand the universe's structure and the formation of galaxies. The idea of cold, dark matter suggests that these particles move slowly compared to the speed of light. This slow movement allows them to clump together more easily, forming the dense halos that surround galaxies and the vast filaments of the cosmic web. Cold dark matter has been the leading theory for years because it aligns well with many observations of the universe's large-scale structure. It explains why galaxies are distributed the way they are and why they rotate at the speeds we observe. On the other hand, warm, dark matter proposes that these particles move faster, closer to the speed of light. This higher velocity would prevent dark matter from clumping as tightly, leading to a smoother distribution of matter in the early universe. Warm dark matter could help explain some puzzling observations, such as why there are fewer small galaxies than our current models predict. If dark matter were warm, it would have suppressed the formation of these smaller structures, leaving behind a universe dominated by larger galaxies. The distinction between cold and warm dark matter isn't just an academic debate. It shapes our understanding of how the universe evolved. For example, if dark matter is cold, it would mean that the first structures to form in the universe were small clumps that eventually merged into larger galaxies. But if dark matter is warm, the first structures would have been larger, and the process of galaxy formation would have unfolded differently. This difference could also affect how we interpret the cosmic microwave background, the faint glow left over from the Big Bang, which holds clues about the early distribution of matter. Scientists are using a variety of methods to investigate this mystery, from studying the distribution of galaxies in the universe to running sophisticated computer simulations. These simulations allow researchers to test how different types of dark matter would influence the growth of cosmic structures over billions of years. While the evidence currently leans toward cold dark matter, the possibility of warm dark matter remains an intriguing alternative that could solve some of the lingering questions in cosmology. As we continue to explore this mystery, one thing is clear: understanding the temperature of dark matter is key to unlocking the secrets of the universe's structure. Next, we'll dive into another piece of the puzzle: how the cosmic microwave background provides clues about dark matter's role in the early universe. Now, let's shift our focus to one of the most powerful tools in cosmology, the cosmic microwave background, or CMB. This faint glow, often called the afterglow of the Big Bang, is a snapshot of the universe when it was just 380,000 years old. It's like a cosmic fingerprint carrying imprints of the earliest moments of the universe, and it holds vital clues about dark matter. The CMB reveals tiny fluctuations in temperature, which correspond to regions of slightly higher or lower density in the early universe. These fluctuations are the seeds from which all cosmic structures, galaxies, clusters, and the cosmic web eventually grew. But here's where dark matter comes into play. While ordinary matter interacts with light, dark matter doesn't. This means that dark matter's gravitational influence shaped these early density fluctuations without leaving a direct trace in the light we see. By studying the patterns in the CMB, scientists can infer how dark matter was distributed in the early universe and how it influenced the growth of cosmic structures. One of the most striking pieces of evidence comes from the way dark matter affects the CMB's temperature fluctuations. Without dark matter, the universe's expansion and the growth of structures would have unfolded very differently. The presence of dark matter explains why the fluctuations we see in the CMB are as large as they are and why they follow a specific pattern. This pattern matches predictions made by models that include dark matter, providing strong support for its existence. But the CMB doesn't just tell us that dark matter exists. It also gives us clues about its properties. For example, the way dark matter interacts with gravity affects how quickly structures formed in the early universe. If dark matter were warm, as we discussed earlier, it would have left a different imprint on the CMB compared to cold dark matter. The fact that the CMB aligns so well with cold dark matter models is one of the reasons this theory remains the leading explanation. The CMB also helps us understand the balance between dark matter and ordinary matter in the early universe. While ordinary matter makes up only a small fraction of the universe's total mass, its interactions with light left a clear signature in the CMB. By comparing this signature with the gravitational effects of dark matter, scientists can measure the ratio of dark matter to ordinary matter with remarkable precision. This ratio is a crucial piece of the puzzle, helping us understand how the universe evolved from its earliest moments to the vast cosmic web we see today. As we continue to study the CMB, it's clear that this ancient light is more than just a relic of the past. It's a window into the invisible forces that shaped our universe. Next, we'll explore another mysterious gravitational phenomenon, the Great Attractor, and how it might be connected to dark matter. Now, let's turn our attention to one of the most puzzling gravitational mysteries in the cosmos, the Great Attractor. Hidden deep within the fabric of the universe, this enigmatic region exerts an immense gravitational pull, drawing galaxies, including our own Milky Way, toward it at astonishing speeds. But what exactly is the Great Attractor, and how does dark matter play a role in this cosmic tug-of-war? The Great Attractor lies in the direction of the constellation Centaurus, about 250 million light-years away. Despite its name, it's not a single object but rather a vast concentration of mass, so dense that it warps the very fabric of space-time around it. For decades, this region remained shrouded in mystery because it sits behind the plane of our galaxy, obscured by dust and stars. But thanks to advancements in technology, we've begun to peel back the veil and uncover its secrets. Here's where dark matter enters the picture. The gravitational pull of the Great Attractor is far stronger than what visible matter alone can account for. Galaxies in its vicinity are moving at speeds that suggest the presence of an enormous amount of unseen mass. This is where dark matter steps in. Scientists believe that dark matter forms a massive halo around the Great Attractor, amplifying its gravitational influence and explaining why it has such a powerful effect on surrounding galaxies. But the story doesn't end there. The Great Attractor isn't just pulling galaxies toward it, it's also part of an even larger cosmic structure. This region is at the heart of what's known as the Laniakea supercluster, a sprawling network of galaxies spanning over 500 million light-years. Dark matter weaves through this supercluster like an invisible web, connecting galaxies and shaping their motion. Without dark matter, the Great Attractor wouldn't have the gravitational strength to hold this vast structure together. What makes the Great Attractor even more intriguing is its connection to the larger cosmic web. Dark matter filaments stretching across the universe funnel galaxies toward dense regions like the Great Attractor. These filaments act as cosmic highways, guiding the flow of galaxies and shaping the large-scale structure of the universe. In this way, the Great Attractor isn't just a destination, it's a key node in the intricate network of dark matter that defines our universe. As we continue to study this gravitational anomaly, one thing is clear: the Great Attractor is a testament to the profound influence of dark matter. It's a reminder that even in the vast emptiness of space, invisible forces are at work, shaping the cosmos in ways we're only beginning to understand. Next, we'll explore another fascinating aspect of dark matter, the mysterious clumps that don't always align with the visible universe. Now, let's shift our focus to another intriguing puzzle in the cosmic dark matter saga, the mystery of dark matter clumps. These clumps are scattered throughout the universe, but here's the twist: they don't always match up with the visible matter we can see. This mismatch has left scientists scratching their heads, and it's reshaping how we think about the distribution of dark matter. Imagine the universe as a vast ocean with galaxies and stars floating like ships on its surface. Dark matter clumps are like invisible currents beneath the waves, guiding the motion of these ships. But sometimes these currents don't align with the ships above. In fact, astronomers have discovered dark matter clumps in regions where there's little to no visible matter at all. This raises a big question: why do these clumps exist independently of the galaxies and stars we can observe? One possible explanation lies in the nature of dark matter itself. Unlike ordinary matter, dark matter doesn't interact with light or other forms of electromagnetic radiation. This means it can form clumps without the need for stars or gas to hold it together. These clumps are held in place purely by gravity, creating pockets of invisible mass that influence the motion of galaxies and other cosmic structures. But here's where it gets even more fascinating. Some dark matter clumps are found in regions that seem completely empty, devoid of any visible matter. These dark clumps challenge our understanding of how matter, both visible and dark, is distributed across the universe. If dark matter clumps can exist without visible matter, it suggests that the two don't always evolve together. This could mean that dark matter has its own rules, separate from the ordinary matter we're familiar with. This discovery has profound implications for our understanding of the universe. If dark matter clumps don't always align with visible matter, it could mean that the cosmic web, the vast network of dark matter filaments connecting galaxies, is even more complex than we thought. It might also explain why some galaxies move in ways that can't be accounted for by visible matter alone. Dark matter clumps could be the hidden architects of these mysterious motions, silently shaping the cosmos from behind the scenes. As we continue to study these enigmatic clumps, one thing is clear: they're a crucial piece of the dark matter puzzle. They remind us that the universe is full of surprises, and that even the invisible forces at work are far more intricate than we ever imagined. Next, we'll dive into another cosmic mystery: the role of dark matter in shaping the vast, empty regions of space known as cosmic voids. Now, let's venture into one of the most fascinating and mysterious aspects of the cosmos: the role of dark matter in cosmic voids. These voids are enormous, seemingly empty regions of space that stretch across billions of light years, making them some of the largest structures in the universe. But don't let their emptiness fool you. These voids are far from being just blank spaces. In fact, they hold critical clues about how dark matter shapes the universe on the grandest scales. Picture the universe as a cosmic sponge, with galaxies and galaxy clusters forming the dense, interconnected filaments of the sponge. The voids are the empty pockets in between, vast and dark. But here's the twist: even in these seemingly empty regions, dark matter plays a crucial role. While there may be little to no visible matter in these voids, dark matter is still present, weaving its invisible threads through these expansive regions. So, why are these voids so important? For one, they help us understand the large-scale structure of the universe. The distribution of cosmic voids is directly tied to the distribution of dark matter. Think of it like this: the voids are the negative spaces in a cosmic painting, and dark matter is the brushstroke that defines their shape and size. By studying these voids, scientists can map out the invisible dark matter web that connects everything in the universe. But there's more to it. Cosmic voids also act as natural laboratories for testing our theories about dark matter and gravity. Because these regions are so empty, they allow us to observe the effects of dark matter without the interference of visible matter. For example, the way galaxies move around the edges of voids can reveal how dark matter's gravitational pull influences their motion. This gives us valuable insights into the behavior of dark matter and how it interacts with the visible universe. Interestingly, cosmic voids also challenge our understanding of the universe's expansion. Dark energy, the mysterious force driving the accelerated expansion of the universe, has a stronger influence in these low-density regions. This means that voids are not just empty spaces, they're dynamic regions where dark matter and dark energy interact in ways we're still trying to fully comprehend. As we explore these vast, empty regions, one thing becomes clear: cosmic voids are far from being just the nothingness of the universe. They're a key piece of the puzzle in understanding how dark matter shapes the cosmos. And as we continue to study them, they may hold the answers to some of the biggest questions in cosmology. Next, we'll turn our attention to another intriguing mystery: the possibility of dark matter particles annihilating each other and what that could mean for our understanding of the universe. Now, let's shift our focus to one of the most intriguing possibilities in the study of dark matter: the idea that dark matter particles might annihilate each other. This concept, known as dark matter annihilation, suggests that when two dark matter particles collide, they could destroy each other, releasing energy in the form of detectable signals like gamma rays or other high-energy particles. It's a fascinating idea that could provide us with a way to indirectly observe dark matter, even if we can't see it directly. But why is this phenomenon so important? For one, it could help us confirm the existence of dark matter particles and give us clues about their properties. If dark matter annihilation is happening, the signals it produces would be like cosmic fingerprints, revealing details about the nature of these elusive particles. Scientists have been searching for these signals for decades, using powerful telescopes and detectors to scan the skies for any hint of this mysterious process. However, despite extensive efforts, dark matter annihilation has yet to be observed conclusively. One reason for this is that the signals produced by annihilation would be incredibly faint, making them difficult to distinguish from other sources of cosmic radiation. Imagine trying to spot a single candle flickering in the middle of a fireworks display. It's not impossible, but it's certainly a challenge. Additionally, the rate at which dark matter particles annihilate might be much lower than initially predicted, further complicating the search. Another factor is that we still don't know exactly what dark matter particles are made of. Are they heavy or light? Do they interact with each other frequently or rarely? These unknowns make it hard to predict where and how often annihilation might occur. Some theories suggest that dark matter annihilation could be more common in regions with high concentrations of dark matter, such as the centers of galaxies or dense dark matter halos. But even in these areas, the signals remain elusive. Despite these challenges, the search for dark matter annihilation continues to be a major focus of modern astrophysics. Experiments like the Fermi Gamma Ray Space Telescope are constantly scanning the universe for any signs of this process, while underground detectors are on the lookout for secondary particles that might result from annihilation. Each new observation brings us closer to understanding whether this phenomenon is real and what it could tell us about the universe's hidden structure. So, while dark matter annihilation remains a mystery for now, it's a mystery that holds incredible potential. If we can one day detect these signals, it would be a groundbreaking discovery, shedding light on one of the universe's greatest enigmas. Next, we'll explore another captivating connection: the relationship between dark matter and black holes, and how these two cosmic giants might influence each other in ways we're only beginning to understand. Now, let's turn our attention to one of the most fascinating intersections in modern astrophysics: the connection between dark matter and black holes. These two cosmic giants, though seemingly unrelated, might be deeply intertwined in ways that could reshape our understanding of the universe. At the heart of this mystery is the idea that dark matter could play a crucial role in fueling supermassive black holes, those colossal entities lurking at the centers of galaxies. Imagine a supermassive black hole, millions or even billions of times more massive than our Sun, sitting at the core of a galaxy. These black holes are surrounded by swirling disks of gas and dust, but what if dark matter is also part of the mix? Some theories suggest that dark matter particles, drawn in by the black hole's immense gravity, could accumulate around it, providing a steady source of fuel. Over time, this dark matter could be consumed, releasing energy and influencing the black hole's growth and activity. But how exactly does this process work? One possibility is that dark matter particles, as they orbit the black hole, occasionally collide and annihilate each other, releasing energy that heats up the surrounding material. This energy could then feed the black hole, helping it grow even larger. Another idea is that dark matter could form a dense halo around the black hole, creating a reservoir of material that slowly trickles in over millions or billions of years. These scenarios suggest that dark matter isn't just a passive bystander. It could be an active participant in shaping the behavior of black holes. this connection might also explain some of the most energetic phenomena in the universe, such as quasars and active galactic nuclei. These incredibly bright objects are thought to be powered by supermassive black holes devouring vast amounts of matter. If dark matter is contributing to this process, it could help explain why some black holes grow to such enormous sizes and why they produce such intense radiation. However, the relationship between dark matter and black holes isn't just about feeding. Some scientists speculate that dark matter could even influence the formation of black holes in the first place. In the early universe, dense clumps of dark matter might have acted as seeds, pulling in ordinary matter and triggering the collapse that led to the birth of the first black holes. This idea ties dark matter not only to the growth of black holes but also to their very origins. Of course, these theories are still in the realm of speculation, and much remains to be discovered. Detecting the influence of dark matter on black holes is no easy task, as both are notoriously difficult to observe directly. But with advancements in technology and new observational tools, such as gravitational wave detectors and next-generation telescopes, we're inching closer to uncovering the truth. The connection between dark matter and black holes is a reminder of how interconnected the universe truly is. What we learn about one could shed light on the other, helping us piece together the cosmic puzzle. As we continue to explore this intriguing relationship, we might find that dark matter is not just a hidden force shaping galaxies. It could also be the key to understanding some of the most powerful objects in the cosmos. Next, we'll delve into another captivating mystery, the origin of dark matter and how it might have formed in the early universe. Now, let's shift our focus to one of the most profound questions in cosmology. Where did dark matter come from? The origin of dark matter is a mystery that takes us back to the very beginning of the universe itself. To understand how dark matter might have formed, we need to rewind the cosmic clock to the moments just after the Big Bang, when the universe was a seething cauldron of energy and particles. One leading theory suggests that dark matter is a relic from the Big Bang, a leftover from the intense conditions that shaped the early universe. In the first fractions of a second after the Big Bang, the universe was incredibly hot and dense, filled with a chaotic mix of particles and radiation. As the universe expanded and cooled, certain particles may have frozen out of this primordial soup, becoming stable and persisting to this day. These particles, according to the theory, could be the dark matter we're searching for. But what kind of particles are we talking about? One possibility is that dark matter is made up of weakly interacting massive particles, or WIMP. These hypothetical particles are thought to have formed in the early universe and then stopped interacting with ordinary matter except through gravity. Another idea is that dark matter could be composed of axions, extremely light particles that were produced in abundance during the Big Bang. Both WIMP and axions are prime candidates for dark matter, but neither has been detected yet, leaving the question of their existence wide open. Another intriguing theory proposes that dark matter might have formed slightly later, during a phase transition in the early universe. Imagine the universe cooling down like a pot of water turning to ice. As it cooled, regions of space might have undergone sudden changes, creating pockets of dark matter. These pockets could then have clumped together, forming the seeds of the large-scale structures we see today, like galaxies and galaxy clusters. There's also the possibility that dark matter isn't a single type of particle, but a mix of different particles, each with its own unique properties. Some scientists have even suggested that dark matter could be made up of primordial black holes, tiny black holes that formed in the early universe. These black holes would be too small to detect directly, but could collectively account for the missing mass we observe. While these theories offer compelling explanations, they also raise new questions. For instance, if dark matter is a relic from the Big Bang, why didn't it interact more with ordinary matter? And if it's made up of multiple types of particles, how do they coexist and influence each other? These are the kinds of puzzles that keep scientists up at night, driving them to develop new experiments and observations to test these ideas. The origin of dark matter is more than just a scientific curiosity. It's a key piece of the puzzle that could help us understand the universe's earliest moments. By uncovering how dark matter formed, we might also learn more about the forces and particles that shape the cosmos. As we continue to explore this mystery, we're reminded that the universe is full of surprises, and dark matter might hold the answers to some of its deepest secrets. Next, we'll explore how dark matter forms the filaments of the cosmic web, connecting galaxy clusters across the vast expanse of space. Now, let's turn our attention to the intricate threads that weave the universe together, the cosmic filaments. These vast thread-like structures are the backbone of the cosmic web, connecting galaxy clusters across unimaginable distances. But what holds these filaments together? The answer, as you might guess, lies in the invisible grip of dark matter. Dark matter plays a crucial role in shaping these filaments. Imagine the universe as a spider's web, with dark matter acting as the silk that forms its framework. In the early universe, dark matter began to clump together under the force of gravity, creating a network of dense regions connected by thinner strands. These strands are the cosmic filaments, and they serve as the highways along which galaxies and galaxy clusters travel. But why are these filaments so hard to observe directly? The challenge lies in their nature. Cosmic filaments are made up of dark matter, which, as we know, doesn't interact with light. This means they don't emit, absorb, or reflect any form of electromagnetic radiation, making them invisible to traditional telescopes. Instead, scientists rely on indirect methods to study them. For example, they observe how light from distant galaxies bends as it passes through these filaments, a phenomenon known as gravitational lensing. This bending of light reveals the presence of dark matter, allowing researchers to map the otherwise invisible filaments. Another reason these filaments are elusive is their sheer scale. They stretch across billions of light years, but their density is incredibly low compared to galaxy clusters. This makes them faint and diffuse, blending into the cosmic background. Despite these challenges, advancements in technology and simulations have given us glimpses of these structures. Supercomputer models like the Millennium simulation have been instrumental in visualizing the cosmic web, showing how dark matter filaments connect the universe's largest structures. Understanding cosmic filaments isn't just about mapping the universe, it's about uncovering the processes that shaped it. These filaments are the scaffolding upon which galaxies formed and evolved. Without dark matter, the universe would lack the structure we see today. As we continue to study these filaments, we're not just exploring the universe's architecture, we're piecing together the story of how everything came to be. Next, we'll delve into another fascinating aspect of dark matter, why it doesn't interact with light and what this means for our ability to study it. This mystery takes us deeper into the enigmatic nature of the universe's most elusive substance. Now, let's shift our focus to one of the most puzzling aspects of dark matter, its complete lack of interaction with light. Unlike everything else we can see in the universe, stars, planets, gas clouds, dark matter doesn't emit, absorb, or reflect any form of electromagnetic radiation. This means it's entirely invisible to our eyes and to the telescopes we use to explore the cosmos. But why is this the case, and how do we even begin to study something that doesn't interact with light? The answer lies in the very nature of dark matter itself. Scientists believe dark matter is made up of particles that don't interact with the electromagnetic force, which is responsible for light and other forms of radiation. This makes dark matter fundamentally different from the ordinary matter we're familiar with. While ordinary matter is made up of atoms which contain charged particles like electrons and protons, dark matter particles are thought to be neutral and unaffected by electromagnetic fields. This is why light passes right through dark matter as if it weren't even there. But if we can't see dark matter, how do we know it exists? This is where indirect methods come into play. One of the most powerful tools we have is gravitational lensing. When light from a distant galaxy travels through space, it can be bent by the gravitational pull of dark matter along its path. By studying how this light bends, scientists can map the distribution of dark matter, even though it remains invisible. It's like seeing the shadow of something you can't see directly, a cosmic clue that reveals the presence of the unseen. Another method involves studying the motion of stars and galaxies. Dark matter's gravitational influence affects how these objects move. For example, stars on the outer edges of galaxies often move faster than they should based on the visible matter alone. This discrepancy points to the presence of dark matter, whose gravity is pulling on these stars from the shadows. By analyzing these movements, researchers can estimate how much dark matter is present and where it's concentrated. Particle physics experiments also play a crucial role. While dark matter doesn't interact with light, some theories suggest it might occasionally collide with ordinary matter. Experiments like LUX-Zeppelin and Xenon-1T are designed to detect these rare interactions deep underground, shielded from cosmic radiation. Though no definitive detection has been made yet, these experiments are pushing the boundaries of what we know about dark matter's properties. Understanding why dark matter doesn't interact with light isn't just a scientific curiosity, it's a key to unlocking the universe's secrets. Without this knowledge, we'd be blind to the vast majority of the cosmos. By using these indirect methods, we're slowly piecing together the puzzle of dark matter, one observation at a time. Next, we'll explore how dwarf galaxies, with their high concentrations of dark matter, serve as unique laboratories for studying this mysterious substance. Now, let's turn our attention to a fascinating and unique corner of the cosmos: dwarf galaxies. These small, faint galaxies might not grab headlines like their larger counterparts, but they hold a special place in the study of dark matter. In fact, dwarf galaxies are often considered the perfect natural laboratories for unraveling the mysteries of this elusive substance. But why is that? And what makes them so different from the galaxies we're more familiar with? The key lies in their composition. Unlike larger galaxies, which are packed with stars, gas, and dust, dwarf galaxies are dominated by dark matter. In some cases, dark matter makes up more than 90% of their total mass. This makes them incredibly valuable for studying how dark matter behaves and interacts with the universe around it. Because there's so little ordinary matter to interfere, scientists can observe the gravitational effects of dark matter more clearly in these galaxies than anywhere else. But studying dwarf galaxies isn't without its challenges. For one, they're incredibly faint. Many of these galaxies are so dim that they're almost invisible against the backdrop of the night sky. This makes them difficult to detect, even with the most advanced telescopes. Additionally, dwarf galaxies are often found in the outer regions of galaxy clusters or in isolation, making them harder to locate and observe compared to brighter, more central galaxies. Another challenge is their small size. Dwarf galaxies typically contain only a few billion stars, compared to the hundreds of billions found in larger galaxies like our Milky Way. This means they produce less light, making it harder to gather enough data to study them in detail. Despite these obstacles, scientists have developed clever ways to overcome them. For example, by using sensitive instruments and long exposure times, researchers can capture the faint light emitted by these galaxies, revealing clues about their dark matter content. One of the most intriguing aspects of dwarf galaxies is their motion. Because they're so rich in dark matter, their stars move in ways that can't be explained by the gravity of visible matter alone. By studying these movements, scientists can map the distribution of dark matter within these galaxies, providing insights into its properties and behavior. This has led to some surprising discoveries, such as the fact that dark matter in dwarf galaxies seems to be more densely packed at their centers than in larger galaxies. Dwarf galaxies also offer a unique opportunity to test theories about dark matter. For instance, some models predict that dark matter particles should occasionally collide and produce detectable signals such as gamma rays. By observing dwarf galaxies, which are relatively free of other sources of gamma radiation, scientists can search for these signals with greater precision. While no definitive evidence has been found yet, these observations are helping to narrow down the possibilities. In the grand scheme of the universe, dwarf galaxies might seem small and insignificant, but they play a huge role in our quest to understand dark matter. By studying these cosmic underdogs, we're gaining valuable insights into the nature of the invisible web that shapes our universe. Next, we'll explore how dark matter might even influence the fabric of time itself, pushing the boundaries of our understanding of physics. Now, let's venture into one of the most mind-bending mysteries of dark matter, its potential influence on time itself. While we often think of dark matter as shaping the structure of the universe, some theories suggest it might also play a role in the very fabric of space-time. This idea pushes the boundaries of modern physics, challenging our understanding of how time and gravity interact. One intriguing possibility is that dark matter could affect the flow of time in ways we don't yet fully grasp. According to Einstein's theory of general relativity, massive objects like stars and black holes warp spacetime, creating what we experience as gravity. But what if dark matter, with its immense gravitational influence, also alters the passage of time? Some scientists speculate that regions densely packed with dark matter might experience time differently than areas dominated by ordinary matter. This could mean that time might flow slower or faster in these regions, though detecting such subtle effects remains a monumental challenge. Another speculative theory suggests that dark matter could be linked to the concept of time dilation, a phenomenon where time passes at different rates depending on the strength of a gravitational field. For example, near a black hole, time slows down significantly due to the intense gravity. If dark matter clusters in certain areas, could it create similar, albeit weaker, time dilation effects? While this idea is still in its early stages, it opens up fascinating questions about how dark matter might influence not just space but time as well. Some researchers have even proposed that dark matter could be connected to the arrow of time, the one-way direction in which time flows from past to future. While this remains highly speculative, the idea is that dark matter's gravitational effects might subtly influence the universe's expansion and, by extension, the way time unfolds. This could provide new insights into why time seems to move in only one direction, a question that has puzzled physicists for decades. Of course, these theories are still in the realm of speculation, and testing them is no easy task. Detecting subtle changes in the flow of time caused by dark matter would require incredibly precise measurements far beyond our current capabilities. However, as technology advances and our understanding of dark matter deepens, we may one day uncover whether this mysterious substance holds the key to unraveling the mysteries of time itself. As we continue to explore these ideas, one thing is clear: dark matter doesn't just shape the universe, it might also shape our understanding of time and space-time. Next, we'll dive into another frontier of dark matter research, its potential connection to quantum gravity, a theory that seeks to unite the worlds of the very large and the very small. Now, let's shift our focus to another fascinating frontier in the study of dark matter, its potential connection to quantum gravity. This is where the mysteries of the very large dark matter and the structure of the universe meet the mysteries of the very small, the realm of quantum mechanics. Quantum gravity is a theoretical framework that aims to unify these two worlds, and dark matter might just hold the key to bridging this gap. At its core, quantum gravity seeks to explain how gravity, which governs the behavior of massive objects like planets and galaxies, operates at the smallest scales where particles behave according to the rules of quantum mechanics. While we have a solid understanding of gravity on cosmic scales thanks to Einstein's theory of general relativity and a robust framework for quantum mechanics at the atomic level, combining these two has proven to be one of the greatest challenges in modern physics. Dark matter, with its elusive nature and gravitational influence, might offer clues to solving this puzzle. One of the biggest challenges in reconciling dark matter with quantum gravity lies in the fact that dark matter doesn't interact with light or other forms of electromagnetic radiation. This makes it incredibly difficult to study using traditional methods. In the quantum realm, particles are often detected through their interactions with light or other forces, but dark matter remains stubbornly invisible. This raises the question, could dark matter be governed by quantum rules that are fundamentally different from those we've observed in ordinary matter? Some theories suggest that dark matter particles might be part of a hidden sector of the universe, governed by its own set of quantum rules. If true, this would mean that dark matter could interact with itself in ways we can't yet detect, potentially through forces or particles that don't exist in our visible universe. This idea opens up the possibility that dark matter could be a gateway to understanding new quantum phenomena, ones that might help us develop a unified theory of quantum gravity. Another intriguing possibility is that dark matter could be linked to hypothetical particles like gravitons, which are thought to mediate the force of gravity in quantum terms. While gravitons have yet to be detected, their existence could provide a bridge between the quantum world and the gravitational effects we see on cosmic scales. If dark matter interacts with gravitons or similar particles, it might offer a way to test theories of quantum gravity indirectly, even if we can't observe these interactions directly. However, the challenges are immense. Detecting quantum effects in dark matter would require experiments of unprecedented precision, as well as a deeper understanding of how dark matter behaves on both cosmic and microscopic scales. Current experiments, like those searching for dark matter particles in underground labs, are pushing the boundaries of what's possible, but we're still far from having a complete picture. As we explore these ideas, one thing becomes clear. Dark matter isn't just a cosmic mystery, it's a puzzle that could reshape our understanding of the fundamental laws of physics. By investigating its potential connection to quantum gravity, we're not just probing the nature of dark matter, we're also taking a step closer to unlocking the secrets of the universe itself. Next, we'll turn our attention to another profound question. What does the future hold for dark matter, and how might it shape the destiny of the cosmos? Now let's turn our gaze toward the horizon of cosmic time and ponder one of the most profound questions about dark matter. What is its ultimate fate? As we've explored, dark matter plays a crucial role in shaping the universe, but what happens to it as the cosmos continues to evolve? Will it fade away, transform, or remain a constant force in the fabric of reality? This mystery takes us into the realm of speculation, where theories about dark matter's future are as intriguing as they are uncertain. One possibility is that dark matter could decay over time. Just as some particles in the visible universe break down into smaller components, dark matter particles might also undergo a similar process. If this happens, it could release energy or produce other particles that we might eventually detect. However, the timescales involved could be unimaginably long, stretching far beyond the current age of the universe. This raises the question, if dark matter decays, how would we ever know? The answer lies in the faint signals it might leave behind, which future technologies could one day uncover. Another theory suggests that dark matter might evaporate, slowly dissipating into the vastness of space. This idea ties into the concept of dark matter being made up of particles that interact very weakly with ordinary matter and even with each other. Over billions or even trillions of years, these particles could drift apart, reducing the density of dark matter in the universe. If this happens, the gravitational glue that holds galaxies together might weaken, potentially altering the structure of the cosmos in ways we can't yet predict. On the other hand, some scientists propose that dark matter could remain a constant presence, unchanging and eternal. In this scenario, dark matter would continue to exert its gravitational influence indefinitely, shaping the universe's evolution without ever diminishing. This idea aligns with the notion that dark matter is a fundamental component of the cosmos, as essential to its structure as space and time itself. If true, dark matter would remain a silent partner in the universe's story, forever influencing its destiny. There's also the tantalizing possibility that dark matter could interact with itself or other forces in ways we haven't yet discovered. For instance, if dark matter particles can annihilate each other, they might produce detectable signals such as gamma rays or neutrinos. While we haven't observed this phenomenon conclusively, it remains a key area of research. If dark matter annihilation occurs, it could provide clues not only about its fate but also about its nature and composition. As we consider these theories, it's important to remember that the ultimate fate of dark matter is deeply intertwined with the fate of the universe itself. Whether dark matter decays, evaporates, or endures, its destiny will shape the cosmos in ways we're only beginning to understand. This mystery reminds us that dark matter isn't just a passive player in the universe, it's a dynamic force that could hold the key to the cosmos's long-term evolution. With this in mind, let's venture into our final mystery, where we'll explore the speculative and mind-bending idea of dark matter's connection to the multiverse, a concept that could redefine our understanding of reality itself. Now, let's take a leap into one of the most speculative and mind-expanding mysteries of all, the connection between dark matter and the multiverse. Could dark matter be the hidden thread that ties our universe to others? This idea pushes the boundaries of our understanding, blending cosmology with the realm of theoretical physics in ways that challenge everything we think we know about reality. One intriguing possibility is that dark matter could act as a bridge between our universe and parallel ones. Imagine dark matter as a kind of cosmic glue, not just holding galaxies together in our universe, but also linking us to other dimensions or universes entirely. Some theories suggest that dark matter particles might interact with forces or particles in these other realms, creating a subtle connection that we can't yet detect. If true, this would mean that dark matter isn't just a local phenomenon. It could be a universal one, stretching across the fabric of existence itself. Another fascinating angle is the idea that dark matter might be a remnant of interactions between our universe and others. In some multiverse models, universes can collide or interact, leaving behind traces of their encounters. Dark matter could be one such trace, a leftover imprint from a cosmic collision that occurred billions of years ago. This would mean that dark matter isn't just a mystery within our universe, it could be a clue to understanding the broader multiverse. There's also the possibility that dark matter particles are themselves travelers from other universes. In this scenario, dark matter could be made up of particles that don't belong to our universe at all, but have somehow crossed over from another dimension. This would explain why dark matter interacts so weakly with ordinary matter. It's not from our universe, so it doesn't play by our rules. If this is the case, studying dark matter could give us a glimpse into the physics of other realms, offering insights into realities beyond our own. Of course, these ideas are highly speculative, and there's no direct evidence yet to support them, but they highlight the profound questions that dark matter raises about the nature of existence. Could dark matter be the key to unlocking the secrets of the multiverse, or is it simply a cosmic coincidence, a puzzle that exists solely within our own universe? Either way, the connection between dark matter and multiverse theories opens up a world of possibilities, challenging us to think beyond the limits of our current knowledge. As we wrap up this exploration, it's clear that dark matter is more than just a missing piece of the cosmic puzzle. It's a gateway to some of the most profound mysteries in science. Whether it's shaping galaxies, influencing the universe's expansion, or potentially connecting us to other realities, dark matter continues to captivate and confound us. And as we look to the future, one thing is certain: the more we learn about dark matter, the more we realize how much we still have to discover. With that, we've reached the end of our journey through the 25 mysteries of the cosmic dark matter web. But the story of dark matter is far from over. As new technologies and experiments push the boundaries of our understanding, who knows what secrets we'll uncover next? The universe is full of wonders, and dark matter is just one of its many enigmas waiting to be solved. As we step into the next chapter of our cosmic journey, let's turn our gaze toward the future, a future brimming with possibilities for unraveling the secrets of dark matter. The quest to understand this enigmatic substance is far from over, and the coming years promise groundbreaking advancements that could reshape our understanding of the universe. One of the most exciting developments on the horizon is the James Webb Space Telescope. This marvel of modern technology is not just a tool for observing distant galaxies, it's a window into the hidden structures of the cosmos. By peering deeper into space and time than ever before, the James Webb Telescope could reveal how dark matter influenced the formation of the earliest galaxies. Its infrared capabilities allow it to see through cosmic dust, offering a clearer picture of how dark matter shapes the universe on the largest scales. Every image and data point it captures brings us closer to solving the puzzle of dark matter's role in cosmic evolution. But the search for dark matter isn't limited to the skies. On Earth, next-generation particle colliders are gearing up to probe the fundamental nature of matter itself. Projects like the High-Luminosity Large Hadron Collider aim to smash particles together at unprecedented energies, potentially creating conditions where dark matter particles could be detected for the first time. These experiments are designed to explore the tiniest scales of existence, searching for clues that might explain why dark matter remains so elusive. If successful, they could uncover new particles or forces that redefine our understanding of physics. Meanwhile, underground detectors continue to push the boundaries of sensitivity. Experiments like LUX Zeppelin and Xenon 1T are buried deep beneath the Earth's surface, shielded from cosmic radiation, to detect the faintest signals of dark matter interactions. These detectors are becoming more sophisticated with each iteration, increasing their chances of capturing a rare dark matter event. Even a single detection could revolutionize our understanding of the universe's hidden architecture. Space-based observatories are also joining the hunt. Missions like the European Space Agency's Euclid Telescope and NASA's Nancy Grace Roman Space Telescope are designed to map the distribution of dark matter across the cosmos with unprecedented precision. By studying how dark matter bends light through gravitational lensing, these telescopes could provide new insights into its properties and distribution. The data they collect will help scientists refine their models of the universe's structure and evolution. Beyond these projects, innovative technologies are emerging that could open entirely new avenues for dark matter research. Quantum sensors, for example, are being developed to detect the subtle effects of dark matter on ordinary matter. These devices operate at the cutting edge of quantum physics, offering the potential to sense interactions that traditional instruments might miss. Similarly, advancements in artificial intelligence are enabling researchers to sift through vast amounts of data more efficiently, identifying patterns that could point to dark matter's presence. The future of dark matter research is a tapestry of collaboration, innovation, and curiosity. Each experiment, telescope, and detector brings us one step closer to understanding this cosmic mystery. And while the answers remain elusive, the journey itself is a testament to humanity's relentless drive to explore the unknown. As we look ahead, one thing is certain: the story of dark matter is still being written, and the next chapter could hold the key to unlocking the universe's deepest secrets. As we venture into the realm of thought and wonder, let's pause to consider the profound philosophical questions that dark matter raises. This invisible force, which shapes the very fabric of our universe, doesn't just challenge our scientific understanding, it pushes the boundaries of how we perceive reality itself. What does it mean for something to exist if we can't see it, touch it, or even fully comprehend it? Dark matter forces us to confront the limits of human knowledge and the nature of existence in ways that are as humbling as they are fascinating. At its core, dark matter challenges the very foundation of what we consider real. For centuries, humanity has relied on observation and experimentation to understand the world around us. But dark matter defies this approach. It doesn't interact with light, making it invisible to our telescopes. It doesn't emit energy, leaving no trace for our instruments to detect directly. Yet, its gravitational effects are undeniable, shaping galaxies, bending light, and holding the universe together. This raises a profound question. If something can't be observed directly, does it still exist? Dark matter suggests that reality is far more complex than what our senses can perceive, inviting us to rethink the nature of existence itself. This mystery also highlights the limits of human knowledge. Despite centuries of scientific progress, dark matter reminds us that there are still vast unknowns in the universe. It's a humbling reminder that our understanding is incomplete and that the cosmos is full of secrets waiting to be uncovered. This isn't just a scientific challenge, it's a philosophical one. It forces us to grapple with the idea that there may be aspects of reality that are beyond our current ability to comprehend. In a way, dark matter is a cosmic mirror, reflecting the boundaries of our curiosity and the endless potential for discovery. The implications of dark matter extend beyond science and into the realm of philosophy. It invites us to consider the nature of the universe and our place within it. If dark matter makes up the majority of the universe's mass, what does that say about the ordinary matter that makes up stars, planets, and even us? Are we merely a small fraction of a much larger, invisible reality? These questions touch on themes of existence, purpose, and the interconnectedness of all things. Dark matter doesn't just shape galaxies, it shapes how we think about our own significance in the grand tapestry of the cosmos. Moreover, dark matter challenges the way we approach knowledge and truth. It reminds us that science is a journey, not a destination. Every discovery opens new doors, but it also reveals new mysteries. This dynamic process of exploration and questioning is at the heart of both science and philosophy. Dark matter embodies this spirit of inquiry, urging us to keep asking questions even when the answers seem out of reach. It's a testament to the power of curiosity and the human drive to understand the unknown. As we reflect on these philosophical implications, one thing becomes clear: dark matter is more than just a scientific puzzle. It's a gateway to deeper questions about reality, knowledge, and our place in the universe. It challenges us to think beyond what we can see and to embrace the mysteries that lie just beyond our understanding. And in doing so, it reminds us that the pursuit of knowledge is not just about finding answers, it's about asking the right questions. With that in mind, let's turn our attention to how dark matter has captured the imagination of popular culture, shaping stories and sparking curiosity in ways that go beyond the lab and into the realm of art and storytelling. Now, let's shift our gaze from the profound mysteries of dark matter to its fascinating presence in popular culture. Dark matter, with its enigmatic nature, has become a staple in movies, books, and television, often serving as a source of intrigue and inspiration. Its portrayal in these mediums not only reflects our collective curiosity, but also shapes how the public perceives this cosmic mystery. From thrilling sci-fi adventures to thought-provoking dramas, dark matter has captured the imagination of storytellers and audiences alike, becoming a symbol of the unknown and the unexplored. In movies, dark matter often takes on a larger-than-life role, sometimes depicted as a mysterious force with the power to alter reality or even destroy worlds. Films like Interstellar and The Dark Matter use it as a central plot device, weaving it into narratives that explore the boundaries of human understanding and the vastness of the cosmos. These portrayals, while dramatic, often simplify or exaggerate the science behind dark matter, creating a blend of fact and fiction that sparks curiosity but can also lead to misconceptions. For instance, dark matter is sometimes portrayed as a tangible, glowing substance, when in reality, it's completely invisible and undetectable by conventional means. Books, on the other hand, often delve deeper into the philosophical and speculative aspects of dark matter. Authors like Philip Pullman, in his Dark Materials series, use dark matter as a metaphor for the unseen forces that shape our lives and the universe. These stories invite readers to ponder the nature of existence and the hidden connections that bind everything together. While these interpretations are imaginative, they also highlight the challenge of translating complex scientific concepts into relatable narratives. The result is a mix of awe-inspiring ideas and occasional misunderstandings about what dark matter truly is. Television shows have also embraced dark matter as a compelling theme, often using it to drive plot lines that explore the unknown. Series like Star Trek and Doctor Who have featured dark matter in episodes that blend science fiction with speculative science, creating stories that entertain while sparking curiosity about the real-world mysteries of the universe. These portrayals, though fictional, play a significant role in shaping public perception, often introducing viewers to the concept of dark matter for the first time. However, they also risk perpetuating myths such as the idea that dark matter is a dangerous or malevolent force. What makes dark matter so captivating in popular culture is its inherent mystery. It represents the ultimate unknown, a blank canvas onto which writers and creators can project their wildest ideas. This fascination with the unseen and the unexplained taps into a deep human desire to explore and understand the universe. Yet, this same allure can also lead to misconceptions, as the line between scientific fact and creative fiction becomes blurred. For many, their first encounter with dark matter comes not from a textbook but from a movie or a TV show, making it crucial for scientists and educators to bridge the gap between entertainment and accurate information. As we reflect on dark matter's role in popular culture, it's clear that its influence extends far beyond the realm of science. It has become a symbol of curiosity, a reminder of how much we have yet to discover, and a source of inspiration for stories that challenge our imagination. While these portrayals may not always align with scientific reality, they play a vital role in sparking interest and encouraging people to ask questions about the universe. And in doing so, they remind us that the pursuit of knowledge is as much about wonder and storytelling as it is about data and equations. With that in mind, let's turn our attention to the future of dark matter research and the groundbreaking experiments that aim to unravel its secrets. As we reach the end of our journey through the 25 mysteries of the cosmic dark matter web, one thing becomes abundantly clear: the universe is far more mysterious and complex than we can fully comprehend. From the invisible architecture that binds galaxies together to the elusive particles that refuse to reveal themselves, dark matter continues to challenge our understanding of the cosmos. Each mystery we've explored, whether it's the role of dark matter in galaxy formation, the enigma of dark matter halos, or its potential connection to black holes, reminds us that we are only scratching the surface of this profound cosmic puzzle. The search for dark matter is not just a scientific endeavor. It's a testament to humanity's unyielding curiosity and determination to uncover the secrets of the universe. Despite decades of research, we still don't know what dark matter truly is, how it formed, or what its ultimate fate will be. Yet, every discovery, every experiment, and every new theory brings us one step closer to unraveling these mysteries. The cosmic dark matter web is a reminder that the universe is full of wonders waiting to be discovered, and that the pursuit of knowledge is a journey without end. So, as we conclude this exploration, let's leave you with a question to ponder. What if dark matter is not just a missing piece of the cosmic puzzle, but a gateway to understanding something even greater? Something that could redefine our place in the universe? The answers are out there, hidden in the vast expanse of space, waiting for us to find them. Stay curious, keep asking questions, and never stop exploring the mysteries that surround us. If you enjoyed this deep dive into the cosmic dark matter web, don't forget to like, subscribe, and hit the notification bell to stay updated on our latest explorations of the universe's greatest enigmas. The cosmos is full of secrets, and together we can uncover them. Until next time, keep looking up and wondering what lies beyond the stars.